Great, we're live on YouTube and I've opened the room to attendees.
Okay, so hello to everybody. Welcome to the afternoon session of the day two, where the day two is electron correlation and quantum interference. Salamanca University here in Spain. Is afternoon here in Spain is 3:31. In Beijing is 9:30 in the night, and in Canada is 9:30 in the morning. So first of all, I would like to thank the organizers for having prepared this very nice meeting. These kind of conferences have now become very usual, but this one I think in particular has been very well organized, and the way the speakers have been arranged and all the topics I think is very good. So I would like to thank the organizer for all this hard work. Today we will have the two talks, and these talks will be on electron correlation. This is there is a lot of open questions still in this field, in the electron correlations, in the presence of a laser field, either strong or an XUV. And we will have two presentations. One is from Jing Cheng from the Institute of Applied Physics and Computational Mathematics in Beijing. And the title of the talks is Interference Effects Challenge in Non-Sequential Double Ionization. And then after we will have a talk by Joe Sanderson, which is entitled The Waterloo ALS Reaction Microscope Facility at the Advanced Laser Light Source. So this is two talks. One of them will be on theory of this very fundamental problem in physics, and the other one will be in experimental one in one of these reaction microscopes, which have played a fundamental role in helping us to understand what is happening in this kind of system. So without further ado, I will just let me remind you that you can ask your questions here on the Zoom chat. You can also post your questions on the Slack, and if you prefer it, also you could just raise your hand, and we will give you the microphone so that you can ask your question. Okay, so now without further ado, I give the floor to Jing Cheng for the presentation. Welcome, Jing.
Thank you. No. Right. Okay. Okay. Thanks, Kevin, for introduction, and also I would like to thank the organizers to organize this very wonderful workshop. Okay, let me share my screen. It's not easy, we know, in this hard time. Let's look out my pointer. Okay, as we heard in the previous sections of this workshop, interference, of course, is a very important effect. But what we have heard is most related to the single ionization or ATI or such kind of processes. This interference, in fact, in the double ionization is not an easy problem. So I will show in this talk that there's still many debates about this effect. What I will talk include many works from the cooperation with many colleagues from different institutions, including Wuhan Institute of Physics and Mathematics, basically the Xiaojun News Group, and also from Shanxi University, Southwest Jiao Tong University, also Wilhelm Baker from MBI in Berlin, and IOP, and also many colleagues of my institute. Okay, I will talk about the so it's 4 parts: background and the rescattering excitation with subsequent analysis process, and some interference effect in the rescattering impact analysis process, and then finally is a simple conclusion and perspective. Non-sequential double annihilation have been first observed almost 40 years ago. Experimentally, people found this iron yard of the double charged iron is much higher than the prediction of the single active electron prediction. Okay, then the mechanism of this process caused many debate in the first about 20 years until this Coulomb has a very powerful facility to measure the differential the observations. Here's the correlation distribution and momentum distribution, which is measured by these Coulombs. With this measurement, and of course, with theoretical calculations and analysis, the mechanism of this process have been decided to be the rescattering, as shown in these cartoons. The electron tunnel analysis, and then it will be accelerated, and it will be scattered with this iron. When the scattering energy of the electron is high enough, then the second electron will be directly analyzed by the collision. On the other hand, if the returning energy of the electron is not large enough, then the second electron can be excited to excited states, and then it can be analyzed by the field. Of course, it can also happen when the return energy is higher than the analyzing potential of the second electron. Theoretically, we have 3 different treatment. TDSC, of course, is very exact, it's accurate, but it's hard to calculate. Quantum model, we need many approximations. So the semiclassical or classical model, now called the CTMC, have been developed and widely used in the analysis. In this semiclassical model or classical model, we treat the electron classically after analysis of the tunneling. This CTMC method has gained great successes in the study of this non-sequential time analysis process. For example, for the momentum distribution, it is in agreement with the experiment, and also for the iron yard of the double charged iron and the single charged iron. Here we observed this kind of typical knee structure in the iron yard, and in some cases, this semiclassical calculation can also quantitatively reproduce the experimental observation. For energy spectrum and correlated distribution, they can all be well reproduced by this classical or semiclassical model. Even for the elliptical polarization and the circular polarization, the semiclassical model or the classical model give a consistent result with the experiment. Recently, this model has also been applied to the wavelength dependence of the non-sequential double annihilation. More surprised, the fine structures observed in experiment in this electron correlation distribution can be reproduced by the semiclassical or classical model, and direct analysis shows the effect of the electron-electron interaction and the electron-ion Coulomb potential effect in this fine structure mechanism. So some people even think that quantum mechanics is not necessary in our analysis or understanding of this non-sequential double annihilation. So what's beyond the semiclassical model? That means what can we observe quantum effect, interference effect in the double annihilation process? There are some difficulties in the experiment. One is the focal average. This effect will largely smear out the subtle structures in the distributions. And one more effect is the null statistics in the Coulomb's measurement. For this coincide measurement, the statistics is quite low. So usually it's hard to have enough number of events to show these detailed structures. So what we expect in the non-sequential double annihilation for this interference effect in the rescattering impact annihilation process, ground and continuum states are involved. So we expect the interference will happen between the different trajectories for the reside channel, since excited states are involved. So there may be some interference between the channels. So at first, let's have a look at the effect in the reside channel. In 2008, Heidelberg's group reported this very interesting measurement for the argon. We can see that this distribution translates from the anti-correlation at low intensity and to anti-correlation when intensity is increased. However, this phenomenon is absent for neon. So we use the quantum model to calculate this process, which is the third order expansion in the matrix expansion. The first one is the annihilation of the first electron, and the second one is the collision and excitation. And the third one is the annihilation of the second electron by the laser field. So when the electron is excited to different excited states, they will interference and to give some effect which can be maybe observed in the experiment. We consider the five channels, different excited states for different intensities. These correlation distributions show state dependence and also intensity dependence. More important, they are all symmetric. So our calculation also show that these three channels play the most important roles. So we make coherent and incoherent sum of different channels. In this incoherent sum, they are still symmetric, but for coherent sum, it becomes asymmetry, and so some intensity tend to be anti-correlated to correlated. One more other effect is to be considered is the depletion. The depletion will lead to correlation when we consider both effects, we can see that this correlation distribution shows a transition from the anti-correlation to correlation. So next, we consider the asymmetry parameter, which is the difference between the yard in the first and the third quadrants minus the that in the second and the fourth quadrant, then divided by the sum of the total yard. You can see that the interference effect will give rise to anti-correlation in spite of intensity, but depilation will give rise to correlation. After we consider both effects, there's a transition from the negative, from the anti-correlation to correlation. And for neon, we also did some calculation, but we didn't observe this kind of transition, which is in good agreement with the experiment. Also, we can know there's also many semiclassical simulations on this topic, which shows that this transition can also be reproduced, and they can be attributed to the multiple rescattering events, and also Coulomb potential, very important role in this process. Then we look at the post-lens effect. The Gatchen's group report a very interesting result for this low intensity with this correlation distribution will transist from a cross shape to anti-correlation when the pulse length increase from 4 femtosecond to 30 femtosecond. Colors group did very interesting works. They considered 6 different channels, and with careful consideration of the weight and phase of these different channels, they can successfully reproduce the experimental observation. That is a transition from the cross to anti-correlation. Here, they considered include the electron distinguishability and the intracycle events and different channels interference effect. For classical or the semiclassical result, there's also many effort. Gatchen's group also present some result in this paper. They use a semiclassical calculation, of course, with the specific scattering angle to reproduce their experimental result. And in this result from the Peixiang Lu's group, they use classical calculation. However, seems they cannot reproduce well the cross shape in the correlation distribution. So the next we consider how to improve our quantum model. It's well known that the Coulomb potential is ignored in the SFA model. For example, for these calculations, this is SFA result, and it's high intensity with 1 parawatt per square, and the distribution focus near the orange, but for subclassical calculation, distribution is far from the orange, but that momentum is well consistent with the experiment. Analysis shows that in the SFA model, the multiple return is largely underestimated because of Coulomb focusing effect. This multiple return trajectories will play a very important role in the process. So how to incorporate this Coulomb potential in this model? Here's I would like to show some result. We consider the transition matrix to be composed of 3 parts. The first part is the turning and the subsequent evolution of the electron. We use the CTMC method. For the second one, we consider the quantum process of the excitation. And for the third, analyzing of the excited states, we use the Coulomb corrected SFA to take into account the Coulomb potential. Here's some result. We consider the first excited state since the intensity is low. So we think this one excited is this state should play the most important role. We can clearly see a transition of the shape from a cross to an anti-correlation. We also calculate this ratio between the anti-correlation and correlation. So this increase with the pulse length and saturated. It is in good agreement with experiment. So why this transition occurs, it can be attributed to the different contribution from the first return and the third return, which shows different distributions in the correlation distribution. The first return result shows that this is a cross shape. This shape depends on the competition between the residual momentum of the electron and the vector potential at collision. For the third return, distribution is anti-correlation. So when the pulse duration increases, we can see the transition from the cross to anti-correlation. So actually we can see there's no conclusion for this interference effect, for this pulse length dependent effect. Next, we go to the long wavelength result. This is experimental result from Liu's group for the xenon with 2.4 micrometer laser field. This correlation distribution shows a very typical correlation. Most of the distribution are in the first and third quadrants. To show some detail or the quantitatively result, we calculate this asymmetry parameter again. We can see these fast oscillations in this intensity dependence of this parameter. At first, we also did some semiclassical simulation, which shows a small curve in this intensity dependence of the asymmetry parameter. There's some oscillations, small oscillations. This is due to the fluctuation in the Monte Carlo calculation method. Then we calculate the model, quantum model. We can see for these two channels, when we coherent sum them, we can see the symmetry broken and the interference effect appears. When we only consider the shortest pair or the first return trajectories, you can see for the rescattering impact analysis channel, there's no oscillations. But for this reside channel, we can see clear oscillations in the asymmetry parameters. However, this period of the oscillation is still much larger than experimental observations. Then we consider the different return trajectories, and the calculation shows that the first one and the third returns play the dominant role. So we calculate their contributions. We can see the asymmetry parameter indeed shows these fast oscillations when we consider the interference between the different return trajectories. This one as well. And when we make the sum of these two channels, we can observe this overall shape is in agreement with previous result, and we can also see this kind of fast oscillation with period in good agreement with the experiment observations. Okay, then This is not, of course, the end of the story. We still have many experimental results actually. If we look closely at the correlation distribution, we can see this small range distribution is very sensitive to the intensity. And we can see some particularly in these distributions. Next, when we consider the rescattering impact analysis process. We considered the electron return with the maximum kinetic energy, which is equal to 3.17 UP, as we all know. This is the energy conservation relationship among the collision. So the residual energy is shared by two electrons. If one electron takes no energy, then this one takes all the residual energy. If we consider the momentum of the two electrons, to consider the shift of the electron vector potential, we see that for this high energy electron is distributed in a specific surface in the momentum space. Here's some experimental result. We can see if we extract the data from this circle, then we can see that actually we got the Anderson cross section of this E2E process from the experiment. Here's some result for the xenon and argon for two different intensities. We extracted this cross section from this circle, and this is the result. You can see some very pronounced figure in these curves. All of them shows the maximum at 108 degree, and it decrease with decrease the angle, and with increased intensity, it will decrease faster and reach the minimum at about 120 to 140 degrees. We use the distorted waveform observation to simulate this E2E process. You can see that the result will produce the experiment date. So how to explain these figures? Actually, this cross-section structure is very similar to the elastic scattering, which shows also this kind of oscillations and the maximum at 108 degree. It's called the Ramsey-Townsend diffraction effect. Let's consider the two trajectories typically. One electron moves around the nuclear clockwise, and the other one moves the anti-clockwise. Then they will interference with each other if they have the same final momentum. If the scattering is 180 degrees, obviously they have the same phase, so it interference constructively, typically, to get its maximum at 100 degrees. So when the angle decreases, there's a phase difference, then this curve will decrease until it reaches a minimum. Okay, based on this observation, we can propose a laser-induced inelastic diffraction method to image the ultra-fast dynamics of atoms, especially for molecules, which is very similar to the laser-induced elastic diffraction method, which has been already widely applied. We also use semiclassical model and quantum model try to reproduce the experimental observation. However, they both failed. This is easy to be understood since here we only consider the Coulomb potential in this quantum model. We know that the scattering upon the Coulomb potential cannot be larger than the 180 degree. So we need to reconsider the short range potential more accurately. Okay, then the conclusion. Like we showed before, interference effect still remains to be explored in the non-sequential dimension processes. There's still only debate on this kind of processes, and new imaging technique can be developed based on the interference effect. And finally, our series still need to develop. Finally, I would like to acknowledge the many from the National Nature Science Foundation and National Basic Research Program of China and key program for science and technology research and project. Thank you for your attention.
Thank you very much for your talk, very interesting talk. We have time for some questions, and we would like to ask everyone if they can send their questions through the Zoom applications, or you can also do by the Slack applications. So maybe in the meantime that we receive some questions, I can ask you one, which is I think basically just I don't know if you answer the question that you posed yourself. Could interference effects could be seen in a classical model? I don't know if I understood you well, that you have a full answer for that.
No, I don't think it can be observed in the classical, semiclassical. Of course, so we are looking for some quantum effect, which is beyond the semiclassical or classical description of this process.
Okay, I'm trying to see whether there are some further questions here in the Zoom. I don't see any at this point, but maybe I can try to make one question related more on the new opportunities of these long wavelengths. I think you already show very well many of the things that have been observed in the near infrared lasers at 800 nanometers. But on top of that, now there are these mid-IR lasers. Then there will be several other effects, and you have mentioned some of them. For example, you haven't mentioned the importance of non-dipole effects. Or for example, I think you mentioned briefly about these multiple collisions being important. So could you comment more on the challenges that will arise when there will be more and more experiments on mid-IR lasers in these systems?
I mean for long wavelengths. Yeah, it's some kind of let me see, more related to for long wavelengths. Usually the UP is large, even for some even low intensity, right? So the kinetic energy of the return electron is very large. So this unless or rescattering impact, I mean E2E process is usually important. So so far we think it's not so easy to find this kind of interference effect in this E2E process, because most important contribution is from the continuum states, so they are mixed together, especially in this Coulomb measurement. The statistic is usually low, so it's hard for you to find some subtle structures. But it's better maybe to find this interference effect in the recite channel, I think. But it is not, we don't need this kind of long wavelengths.
Okay, I am checking here in the Zoom, and I don't see any other question at the moment. I don't know in the Slack channel.
I see one from Nakala.
Okay, please go ahead.
So my question is related to your model, including the Coulomb potential. Thank you so much for pointing out that quantum interference is important, first of all, in some regimes of NSGI. And second, I realized that so far you have done only a single channel contribution, but we both know that interchannel interference can be important. So do you intend to extend your model to that? And have you done any comparisons?
Yeah, we are considering that it's important. In fact, as I mentioned in the talk, for this low intensity, it's about 100 terawatts per square meter. So we think this first excited state should be the most important one. And you can see that even with this single channel, we can reproduce qualitatively this experimental observation. That means here maybe the interference effect may not be important. Of course, your suggestion, of course, is very important. We are doing these kind of calculations to look at the interchannel interference and also other relative effect. Thank you.
Thank you. Also, one question I would have is, what, in your opinion, is more important in this regime, quantum interference or the role of the Coulomb potential? Because we know both break the fourfold symmetry you get with the strong field approximation. But it's a difficult question. Which one would play a more important role?
It's good, and as you said, difficult question. It depends, I think. If, for example, as you mentioned, for higher intensity, I think if more channels are involved, the interference will be important. Of course, it's hard to say which one is more important.
Okay, so thank you very much for this. I think at this point we can close this talk and go on to the next talk. And for the next talk we have Joe Sanderson, and the title of the talk is New Waterloo ALL's Reaction Microscope Facility at the Advanced Laser Light Source, Montreal. So Joe, the floor is yours.
Hello, can you hear me okay? See me? Okay, so I'm going to share my screen. First of all, I'd like to thank the organizers, Carlo and her team, for organizing a really nice online conference and for inviting me. And I would like to just say that let me see, where's the pointer? Okay. I'm not actually going to present any experimental results on the topic of the conference, so I just want to clear that up before anybody is disappointed. Really, my talk is going to be to some extent an announcement or an advertisement, if you like, for this new Waterloo Alls facility. And what I will do is I'll talk about that at the beginning of the talk, and then I will talk about some of my kind of personal motivations for getting this new facility working and running, which don't really have any bearing on quantum interference. So apologies for that. So there's lots of people just want to thank for being involved in the work that I'm going to show here. So I'm going to show some oldish results, which I think are still quite important. Okay, so before I start, though, I just want to give you a couple of pieces of information, because I think it's always important to tell people where is the University of Waterloo. This is a map of North America, and Waterloo is where the end of that little arrow is there. It's slightly over to the west of Toronto, and the other lab that I'm talking about here is the Advanced Laser Light Source, or ALLS, which is in Varennes, which is just outside of Montreal. Another important thing to do before I start really is to just acknowledge the fact that the University of Waterloo is situated on First Nations land, and in particular the Anishinaabe group. And so it's a very important thing in Canada that we recognize these areas, these rights. Okay, so here's the punchline really of the talk. It's probably going to be quite a short talk. In 2017, the Canadian Fund for Innovation approved a $12 million upgrade to the Advanced Laser Light Source in Montreal, a facility headed by Francois Legarre. And this application included institutions in Canada such as NRC, University of Ottawa, and University of Waterloo. And an important part of that application from University of Waterloo's point of view was this Waterloo ALLS reaction microscope, which is a kind of facility within the facility, which is jointly managed by Waterloo and ALLS. And this was funded in 2017, and the timetable for it becoming available to users was something like 2020 to 2021. So obviously we're looking at 2021 now. And this is a typical commercial reaction microscope system produced by this company Runtech. And the one of the important aspects of it is that it includes two detectors which have low dead time. So it means that you can hopefully detect more ions and electrons in coincidence. So this is a fairly standard piece of experimental equipment these days, and really it relies on the fact that the laser systems themselves are going to be upgraded. And so one of the new laser systems, I'm not going to go into too much details about these, but one of them is a fiber system, and we've heard discussions about these new high repetition rate, high power fiber lasers before in the conference. So this system is nominally at 2 millijoules at 100 kilohertz, and the ALLS team have pioneered the technique of stretching, using a stretched hollow core fiber to generate either few cycle pulses or shorter pulses. This is a little bit of a paper from a couple of years ago, 2018, where they're taking creating a few cycle pulses with 6 meter long fiber. So that's just the pump that, and that then pumps another couple of laser systems, OPCPA and AO PDF systems, giving and again these are kind of estimates of the current best estimates, but there will be a attosecond beamline as well as this, all of which are going to be running at very high repetition rates. And this is the really the important aspect, along with the new wavelengths that are available. So if as I say, this is actually a user facility, and so if anybody is interested to maybe use this facility to look at some of these interesting quantum interference effects, etc., then please do contact me, and we can discuss how that could happen. There are other experimental end stations, of course, in the facility, and Haida is the person to contact there directly at ALLS. Okay, so that's my little ad for this new facility. And I just talk a little bit about my motivation for this, because back in 2014, we were doing experiments on proton migration imaging in the acetylene molecule. So this is my background. It's really imaging of the nuclei rather than the electrons in the system. So here we look at this acetylene molecule, specifically ionized to the first ionization stage, and that's quite an important aspect. I'll come back to that in a second. Basically, the proton from one end of the molecule makes its way to the other end and becomes a stable molecule known as vanillidine. And it's a really nice example of this process, which is fundamental for so many different chemical reactions and life itself. Just to give it a good background. So what we did in the experiment is we used a 266 nanometer pump laser, which was kind of third harmonic from the 800 to excite and ionize specifically into this first excited state of the singly ionized molecule. This is important because if you just go to the ground state of the 1+ molecule, it doesn't undergo proton migration. So then after that, you can watch this wave packet moving and the molecule changing from the linear to the first an intermediate state before it reaches vanillidine and crosses the conical intersection. So this represents here the probe pulse, sorry, at different times. So this is the scheme here. So you come along first with the 266 onto the acetylene, and second with the probe pulse 800 onto the moving molecule. And then finally, we observe a triply ionized molecule, which is broken up into 3 fragments. So this is where the ion side of the reaction microscope comes from. This is what we were using at the time. And in order to actually kind of quantify how much of this proton migration is taking place, then we basically look at everything in the frame of the CH+. So we create a CH+, a C+, and an H+, and measure the momentum of the H+ relative to the CH+, which is always along the x-axis. The red here means there's a lot of signal. So as you'd expect, the molecule starts off straight. After some time, blue here means that we've lost signal in the linear molecule, and it's got this more bent structure. And then still further on, the vanillidine is more formed fully. And then just by dividing those Newton plots in half, we can say where the acetylene turns into the vanillidine and measured the time scale of that. So this is a nice experiment, and it was published in Nature Communications. We even made a movie of it and compared it with a horse. But the statistics were not as good as we would like them to be. This was done with a 5 kilohertz laser system and a basic delay line detector with significant dead time. We would like to repeat this and also keep the information there from the electrons as well. And so now where are we now, or soon, or next year, or sometime in the future? Nobody really knows, thanks to the pandemic. But we're looking at a 100 kilohertz system with minimal detector dead time. So this is going to be useful for not just for this kind of work, but also for these nice quantum interference type experiments. Okay, so that's a rather short summary of what we've been doing, and hopefully it's something which people will be interested in. And yeah, thank you very much. And for my next talk, you can ask me about what it's like to try and survive the Nobel Prize for your lab colleague. Thanks very much.
Thank you very much, Joe. Thank you very much for the talk. So we have plenty of time for questions and answers. I remind you that we can get your answers from the Zoom channel and also from the Slack channel. So maybe I can start and just asking a very simple question. Well,
yeah.
This new system, 2 things. One is that do you expect a 20-fold increase in the number of counts that you will get because you went from 5 kilohertz to 100 kilohertz? And the other one is related to the previous talk that when you go to these mid-IR wavelengths, then the particles become much more faster. And if you want to see this interference effect or slight features on this, then you will need probably two challenging things. You will need high resolution and also so very large limits. I mean, you will have to accept very large velocities of the electrons. So this system, what did the system could cope with this?
Okay, that's a good question. So at the moment, the configuration of the system is open to negotiation and discussion with people. So this is one of the reasons I wanted to talk about it at this conference. Yeah, because it's one thing to set it up for one kind of experiment, and then that might not optimize it for another. I mean, it's reconfigurable to some extent, but we're not experts in this particular piece of kit. So I'm sure that we're gonna find the issues with trying to do that kind of thing. But maybe we can find a kind of a happy medium which allows us to cover a range of different experiments. As far as the factor of 20 count rate, I'm certainly hoping that something like that is achievable. We'll have to wait and see how that turns out. In the past, we've kind of developed algorithms to try to help us to push the count rate as high as we can without having issues of too many ions. So hopefully the new hexagonal detection system will help us to detect more of the fragments from the ions, which is what you need for a coincidence to be working well.
Okay, so maybe while we wait for some other questions, maybe it's also a related question on the amount of data that you will have to collect, because now if you increase the repetition rate that much, and normally Coulomb stores already big chunks of data, and then you will have more channels to, would you need a very sophisticated infrastructure to deal with that?
Yeah, that's a great question. That's one of the issues that we're struggling with at the moment. As I showed you on the map, Waterloo and Montreal, and it's not like I can drive there in the morning and pick up a hard drive and take it back to Waterloo. So we'll need to have quite a bit of kind of onboard memory and storage there in ORS. But we kind of envisaged doing some kind of cloud analysis. So we'll see how that turns out. But there's definitely opportunities for developing quite substantial data handling systems, actually. So we're trying to work with Google. We have a Google in Waterloo, and maybe they're interested in helping that. It's maybe not the kind of data that they're interested in, but you never know.
Okay, so I think we don't have any further questions. At least I don't see it over here. But then before we finish, let me just do two things. The first one is just to thank the speakers for these very nice talks, and thank you for the time. And also maybe just one last question from my side, and then I will hand out to Bridget Cooper, which have an announcement. And just I would like to say that this online conference, I think it's just because we are not able to travel around the world as we used to do. But maybe in the future, we could have something which is a sort of a mixture between a conference where people is there and we can talk to people and have a coffee with them. But this kind of meetings, maybe we should keep them for trying to save a little bit of CO2 plus into the atmosphere, CO2 into the atmosphere. So yes, with this I will handle this to Bridget Cooper, which has an announcement for you. Bridget.
Hi, thank you. Just a really quick announcement about Twitter. We have some beautiful posters over on Twitter, and you can check them out also via our Slack channel, the Twitter feed. There's plenty of time to still add your poster. If you use the Quantum Battles handle or the hashtag Quantum Battles, we'll be able to find your poster and be able to share it. And just to show you some of the posters that we've had so far, and you can see that they're in a wide variety of topics. And yes, if you head over to Twitter or head over to the Slack channel, Twitter feed, you'll be able to interact with the posters. Secondly, we'll be running some games again in the coffee room, which you can again find on the Slack channel. We'll be having another go at Attoscience Scribble. It'll be a little bit more challenging than yesterday, as we're going to have all the words from Attoscience. But we hope you can join us and have a bit of fun. Thank you.
I would like to make a quick remark. Thank you, Bridget, and thank you all for your huge work on this. We were actually very happy that the conference is going well, and next year we would like to organize a hybrid conference on the same style, Quantum Battles 2021. And one thing we are really, really, really pleased about is that we don't have only the usual participants. We're getting a lot of people from Asia. We're getting a lot of people from South America. We're getting participants from countries which are normally underrepresented. And we are really happy to see that by going virtual, and because we were forced to go virtual during the pandemic, the conference has become much less Eurocentric and is much more inclusive. So I would like to give a huge thanks for all of those who are watching right now.
Okay, so thank you very much for this. So I think with this we can close the session for today, and thank you everybody for watching. See you.